Okay, let's continue. So we have been looking at making flash ADC, and in the last class we saw a technique to improve the resolution of flash ADC without actually having to double all the resources required. So the idea is interpolation. So I hope I have this somewhere. Yeah, essentially the goal is to go and introduce an additional set of reference voltage between existing two reference voltages to increase the resolution by 1 bit. And in the voltage domain we can do this by essentially getting rid of an additional preamplifier by averaging the outputs of two preamplifiers, right? And in a differential implementation this is even more elegant like this, and you can actually interpolate by a large factor to get larger interpolation also. But here the main limiting factor is the mismatch in the gains of the two preamplifiers. That is not possible to guarantee, simply because the input swings this amplifier sees will be completely different from the swings this one sees. It is not possible to properly match. But then we saw how this interpolation can be done in a more efficient manner in time domain, and this idea stems from the observation that if the input voltage lies in this bottom range, the top comparator finishes its decision faster than the bottom comparator, and vice versa when the input is lying in the top range. So by looking at this information as to which of the two comparators finishes the decision first, we can get an extra bit of information as to whether the input is here or here, right? And then we saw this also we can, this time comparison can be done using a simple NOR based SR latch. This will tell you which of the two signals goes to 0 first, and we could also basically extend it for more bits, and for that, as we saw, we need to compare with more reference voltages. So which means we should no longer be checking which comparator finishes first. We should see if one comparator finishes a particular delta t seconds before the other. So if you want to increase the interpolation factor, you will have to introduce more and more levels like this. So which means you have to check for multiple times, and this you can do using TDCs. Again, that's not the scope of the course. Cool. But even with all this circus, we saw with real practical examples that maximum resolution we saw was about 6 bits. Beyond that, it is not practically done. So that's about it. So if you want to get a higher resolution, we will have to look for different architectures or other techniques, and that we will do after the mid-semester. So again, before completely abandoning flash, let's do the following today. See, one bad thing about flash is the number of resources keeps exponentially increasing with resolution. But what was one nice thing about flash? Yeah, that's why it's called flash ADC. It gives the decision instantly, right? So we'll see if we can do something to improve its strength. That's how we typically operate. You have something, you analyze its weakness, strength, you try something to address its weakness and enhance its strength. So today we will see if we can enhance its speed by some technique. And of course this technique, although I am saying for flash, it's a general principle, you can use it for anything. So let us say now you have designed a flash ADC. Let's say it's running at 1 gigahertz. And let us say you are designing it a particular CMOS process, and in that technology you have designed the fastest flash, and that is at 1 gigahertz. Okay. So which means if this is the continuous time analog signal, you are essentially sampling, say, these time instants. And what is the time interval between any two adjacent samples? 1 nanoseconds, 1 by 1 gigahertz. Fine. But now let us say you want to increase the increase the speed to 2 gigahertz. So which means in addition to these blue samples, I'll also have to take these samples. So how can you do this? I just have a flash ADC running at 1 gigahertz. It can only take samples with 1 nanoseconds time resolution. So if I want to get 2 gigahertz sampling speed with just 1 gigahertz flash ADC, what you can do? Yeah, again, the idea stems from the observation that even the time interval between these two additional samples is still 1 nanoseconds. So in principle, you can use another flash ADC. So I'll take an identical flash ADC here. Right? You feed the same input. This is also operated at 1 gigahertz. But what is the difference? Yeah, the sampling time instance between these two is staggered. And how much should I delay this by? Huh? Yeah, and what is the time here? 0.5 nanoseconds, right? So which means if I feed in a clock of say phi of t, to the bottom one, I'll feed phi of t minus 0.5 nanoseconds. Fine. And to get the combined output finally, all I have to do is the first output I'll take from the first ADC, second sample I'll take from the second ADC, third sample I'll take from this, and keep alternating. That is basically a simple multiplexing in digital. The odd samples you basically get from the blue one, the even sample you get from the green one. And again, this something we saw with N-pass filters also, how to increase the sampling rate. So which means if I go and put this in a black box and sell it to you, to the outside world it will look like you have gone and designed an ADC at 2 gigahertz. So this technique is called time interleaving. So in particular this is called 2x time interleaving for obvious reasons. So now of course you don't necessarily have to stop at 2x interleaving, you can extend this to any value of n, and let us say now you have an ADC that can sample at fs by n, but you want to realize an ADC effectively sampling at fs. What would you do now? You put n of the ADCs in parallel, so you'll have n identical copies. Yeah, we'll come to that. Yeah. So let us say this is the first ADC. It is clocked at some phi of t. At what time instance will this ADC sample the signal? Let us say this starts from 0. I'll get the 0th sample. What will be the next sample this will give me? I'm sampling at fs by n. So the next sample will be NTS. Fine? I mean 1 by fs by n. So next will be 2 NTS, so on. So how should the clock to the second ADC be? Should I give the same clock? No. So what should I? How much should I delay it by? I mean, if 1 by NTS. Why do you want TS by n? What is effective sampling rate I want? Fs. So which means my final sampling time period is what? No. I mean, final ADCs needs to sample at Fs. So sampling time period should be TS. So how should this be delayed now? I mean, yeah, this is giving you 0 n to n. But I also see, if I have only one ADC, I am giving n to n like this. But I want 0, 1 TS, 2 TS and so on. So what will I do to this guy? I mean, okay, fine. Why 1 by n? Again, this is what you want, okay? I mean, this is what the first ADC is giving you. You divide this by n, so that becomes TS. Fine. So now, at what time instance will this ADC sample now? It is starting at TS. Next will be? No, it's not 2 TS. N plus 1 TS, right? The time, I mean, basically the time period of sampling for each ADC is NTS. So similarly, if I have the third ADC, what will be the clock to that? 2 TS, so on. And for the last one, it cannot be NTS, right? NTS n minus 1 TS. Fine, that's all. So again, to get the final combined data, what I have to do here now? Yeah, first output is from this guy, second output is this guy, so on. Nth output is from this guy, and then you keep circulating. Same thing, you are going to multiplex again. You keep taking the outputs of each ADC serially and keep doing this. Right? Just an extension of the 2x interleave, and this is called NX time-interleaved ADC. If you short it, that is not correct. Right? Basically, if you have shorting it, this node is basically driven by all of them, right? At different times. Yeah. This is not electrically right way to model this. What you're saying, you understand it correctly, but this is not the electrically right way to model this, right? That is multiplexing. This idea clear? It should not be that alien, right? See, this is how all companies operate. In company, you want some work to be done 24/7. It is not humanly possible to hire one employee and ask him or her to work 24/7. What do? You hire, let's say, one guy starting from morning to afternoon, one guy from afternoon to evening, one guy from evening to midnight, one more guy from midnight to early morning. So that way, one employee is not working continuously. He is working for some short hours, but looks like the work is getting done round the clock. The same thing here. Yes.
In order to sample it at higher frequency, they all should be working simultaneously, right?
No, that's the thing, right? You don't need to. Take this shifting business as an example, right? You want some work to be done 24/7. You hire one employee who is working from morning 6 a.m. to 12 p.m. The second employee need not be working at that time. He can start at 12 p.m. He will start from 12 p.m. to, let us say, evening. One more employee will do from 6 p.m. to midnight.
Yeah, but the frequency of work will be
same. Correct. Here also same, right? They are Fs by n. Right? They are not running 24/7. They are running for short times.
Okay. So we sample it at some intervals. Then we wanted intermediate samples.
Yeah.
We use some other ADC.
That's all. That is basically shifting operation in companies. It doesn't matter, right? These clocks, basically what you mean is these can overlap, no point, right? No issues, right? Because correct. There it was because if you remember from N-path filter, that overlapping clocks was required to get rid of the addition. There also, if you had correct, yeah.
So here we can can't actually say that we can short all of them.
Well, the point is, if you short them, you are all getting at the idea, but these are all digital outputs. Each will come at only one time instant, right? For example, the first ADC will give you some data like this. Okay, this is 0, this is NTS. Now the second ADC will be, let's say at TS, it will start operating. Now if you short them, it will look like at this point, the first ADC is also having something, second ADC is also having something. That is not possible. So you have to multiplex. The idea is clear, right? Integrities, it's okay. Correct. Yeah. This multiplexer will have to operate at the final sampling rate. So first, the first sample is here. TS after you select this ADC, 2 TS after you select the third ADC, and so on. And this is how in practice all high-speed ADCs are all designed. Okay. And in which application have you heard the maximum speeds? Gaming application. What kind of speeds have you heard? Okay, CPU processor, how much? What's the speed you have heard for CPU processors? Few gigahertz. Have you heard anything? That's pretty small. Even Wi-Fi Bluetooth will operate at higher rate. Wi-Fi second standard is 5 gigahertz. That is nothing. I mean, what is the speed of your LAN? No, okay, wireless is actually pretty bad, right? Because, yeah, see, satellite or any wireless communication, you're transmitting through air. You'll have a lot of losses. So, a lot of redundancy and stuff needs to be there. So, speeds are not that fast there, right? I mean, remember that if you keep increasing the speed, if you increase the frequency, basically the distance you can cover is also shorter. So, if you increase the speed, distance is getting shorter. So, what applications will require high speed? Huh? Yeah, optic fiber or any wired connection, right? The internet, USB, whatever, right? You have heard USB, PCI expansion, and LAN. These are the places you need really high speed, going from tens to hundreds of gigabits per second, and this is where these interleaved ADCs are used. I mean, of course, we can think in USB. I mean, I'm just copying a data, just ones and zeros from a PC, and copying it to another memory which is also storing ones and zeros. There is analog mixed signal coming there, but turns out, I mean, you are transmitting ones and zeros, agreed, but let us say this is transmitter receiver. You are connecting the transmitter and receiver for transmitting at really high speeds. This is not a short circuit. This will have a distributed R, L, C, everything. You will have a whole bunch of things operating. So finally, you need to have a dedicated transmitter and a dedicated receiver here at the peripherals. Only then you can make this data transfer possible. And these high-speed ADCs will sit at the receiver end, and loosely speaking, its job is to just see if the received bit is 1 or 0. That is the layman's explanation. Okay. So what I mean, you think that it's all digital, but all data copying at peripheral, you have whole bunch of analog mixing, and these are called actually wireline communication. It's a separate topic by itself, and they usually call it a SERDES, meaning serializer and deserializer. Again, it's a different topic. But you get the idea, right? Cool. So at this point, I thought you guys will ask me a question. So as usual, since you are not asking, I'll ask it and answer myself. So let's say you take a 2x interleaved ADC. Let us say it is running at fs by 2. I have the second ADC also running at fs by 2, and then I multiplex this and take. What is the effective sampling rate I achieve here? Fs. This is my final sampling rate. Right? Let us say this is the input y, output v. So if the effective sampling rate of this ADC is fs, what is the maximum signal bandwidth I can have at the input? Fs by 2. So I'll mention here. So now see, my input can have a maximum bandwidth of fs by 2. But in each of the sub ADCs, I am sampling at fs by 2. So are we making Nyquist happy or unhappy? So will there be aliasing or no? There will be aliasing. But when I say that I am sampling at fs, there should not be aliasing, right? So again, this we saw in time domain. We came to this, and in time domain we saw this is foolproof, no monkey business. We need to sample at some sampling period. We are sampling at that sampling period finally. But it looks like in each individual sub ADCs there will be aliasing. So what do you think is happening?
Right, so the first ADC is missing some information, which will be rich to samples, but the other ADCs.
Yeah, that's exactly how we saw in time domain. That's correct, right? But the question is, if I look at the same scenario in frequency domain, individually I seem to have sampling. Finally, I mean, individually there is aliasing, but finally there is no. So
We are sampling at different times in the time delay, and because of phase shift.
yeah, that's exactly. So again, anytime the simplest explanation is the right explanation, like Sherlock Holmes says. So here there is aliasing, here there is not. So something must be happening when I combine this and take it, and that's what is happening. It indeed gets cancelled, as he's pointing out. So for that, let's actually look at this. So let us say, let me try to model this mathematically. Okay. let us say I have the top ADC sampling at fs by 2. So if sampling operation, how I can model it mathematically? Multiplication with an impulse train. Let us say this is some p delta of t. What is the time period of this impulse train? It's sampling at fs by 2. Time period is 2 times ts. Right? Now I have the second path. That is also sampling at fs by 2. But what is the difference between this and this impulse train? There is a time shift. And how much is the time shift? Ts. But this is also periodic at 2 ts. Now finally, if I were to model this correctly, you can think of it as these two signals are getting added, so that finally I have things sampled at fs. Fine. Now again, the maximum signal frequency, the sampling rate is fs. So the input can have a maximum bandwidth of how much? Fs by 2. So let's say I take the triangular spectrum. We often use it because it's easy to draw. So let us say this is spanning. Okay. This is the input spectrum. Now this is the impulse train, periodic at 2 ts. In the frequency domain, how will it look like? That is also an impulse train. What will be the frequencies at which I'll have the impulses? Time period is 2 ts. So fs by 2, yeah, so we'll have impulses. Let's say I look at positive alone, starting from 0, fs by 2, fs, and so on. This is where my impulses will lie in frequency domain. So now I am basically multiplying the signal in time domain. Frequency domain, what happens? It gets convolved. So I am convolving this spectrum with an impulse around 0 that just comes directly. Actually, erase this. So let's say that comes directly like this, minus fs by 2, 2 plus fs by 2, this is 0. I have this getting convolved with an impulse around fs by 2. That will get shifted. Yeah, correct. That will shifted around fs by 2. So I'll draw it like this. And as you see, there is clearly aliasing happening. And when I convolve with fs, this is basically fs now. Fine. And this will keep doing this. Okay. And as you see, there is aliasing for sure. Now let's see what's happening in the bottom path. We'll push it up slightly. So this is again an impulse train, periodic at 2 ts. Frequency domain, what will it be? Impulse train. What frequencies I'll have the impulses here also? Same, right? I'll have impulses at 0, fs by 2, fs, and so on. But what do you think will be the difference in the spectrum? In time domain, I have a delay. In frequency domain, what happens? Yeah, it's as though I'm adding a phase. So for each of them, e power minus j 2 pi f times ts. Okay, correct. So let's see, right? So for impulse at this frequency, what is the phase added? F is 0, 0 phase. So I can say amplitude is 1, phase is 0. For this fellow, if I put f as fs by 2, what do you get here? E power minus j pi. That becomes, for this, it will again be plus 1. Fine. So now let's look at the spectrum for at the output here. So here again, this spectrum is going to get convolved with these impulses. So impulse around 0, it's going to come directly. Okay. Yeah, so the impulse around fs by 2, when I convolve with impulse around fs by 2, this will get shifted to this frequency. but it will get scaled with the negative thing. So basically I'll have something like this. And the next one will do this. So finally when I add the two, this exactly gets cancelled. Okay. So which means, let's see, if at the input I feed in a sinusoid at f in, at what all frequencies I will see the sinusoid here. I mean, now instead of a triangular spectrum I am considering a sinusoidal thing. So input is also an impulse now, not doing anything significantly different. The input is having two impulses at minus f in and plus f in. Okay. At what all frequencies I will see the impulse here? I will have one at f in. Remember, this spectrum is getting convolved with these fellows. So with zero shift it is coming directly, that is something you want. And you will also have something at fs by 2 minus f in. Same thing will happen here also. I will have f in, fs by 2 minus f in. So you will have this aliasing part, but it turns out if I do this 2x interleaving, so in each sub ADC I will have this tone at fs by 2 minus f in. This is going to be present in each of the sub ADCs, but when I finally combine it, it combines like this: 1 plus c power minus j 2 pi by 2, this becomes 0. Okay. Basically the time delay is introducing a phase shift, and that is doing the magic. So the same happens for an n-channel interleaved ADC also. So let us say now you have, is this clear? Shall I move on? So let me take an nx interleaved. So this is the first one, phi of t. This is the second ADC, phi of t minus ts. Each of the sub ADCs is sampling at fs by n. So once again here, if I feed in a sinusoid at f in, I am sampling at fs by n. At what all frequencies I will see the aliasing parts? Okay, let's do this way. Phi of t, I mean, or let's say the p delta of t here, it's going to be an impulse train. And what is the time period of the impulse train for this fellow? N times ts, fine. So the impulses will be located at what frequencies? 0, fs by n, 2 fs by n, and so on, right? So essentially k times fs by n, fine. Now if I feed in a sinusoid at f in, it is going to get convolved with all of these. So where all will I see the tones here? I mean, okay, if it's confusing, see here we saw this fellow. I had impulses at 0, fs by 2, so on. So this got shifted and we got these. Fine. Now I have the same thing. I will have impulses at the input at minus f in and plus f in. That spectrum is going to get shifted around each of these. What all frequencies I will see? I will definitely see one at f in. That is something you want. And then I can generally write it like this. Fine. And for this, I mean, this is basically the required part. This is the unwanted part, and for this fellow k will go from 1 to n minus 1, because k equal to 0 we have already taken as f in here. Is this fine? I mean, the idea is again for each of the sub ADCs, the sampling is happening at fs by n. So impulse time will be at k times fs by n. At the input, you have two impulses at plus f in minus f in. That spectrum will be shifted around k fs by n. So you will have around this frequency. Now for k equal to 0, this will be at fn. That I have taken out separately because that is something you want, and written the other unnecessary components. Well, after that it's, I mean, yeah, the idea is after that you have fs plus something. Fs plus something when you are finally, this is effectively sampling at fs. We'll only look at till fs by 2 here. And okay, these are typically called interleaving images, the unwanted stuff. So once again here at each of these sub ADCs we will have these interleaving images, but finally when you add it, it gets cancelled and we can see, right? So let us say in the first path there is no delay, so it's basically 1. In the second path there is a delay of Ts. For a sinusoid f, sinusoid at a frequency f, what will be the delay introduced by this or phase introduced by this? Fine. I mean, since it's getting delayed in time, in frequency domain introduce this phase, and for this it is basically f times n minus 1 Ts. So now let us see how things are getting cancelled here. So now what do you think will be the, I mean, for the first path, phase is always 0, no confusion. So what do you think will be the phase introduced by this path for this image frequency? Yeah, remember when I had 2x time-interleaved ADC, I had impulses at 0, fs by 2, so on. I was checking the phase at these frequencies. Now I have impulses at what frequency? Yeah, so on. So I should be checking the phase at what frequencies? At this kfs by n. Okay, this clear? See, in the 2x interleaved ADC, I had the impulses at these.
By using the impulse rate, we use T minus Ts.
Correct.
So like, shouldn't we have used like the twice of Ts because we have to sample at fs by 2 eventually?
No, I mean, why are you getting confused? You have some signal. I am taking 0 and NTS. The next ADC should take at TS. Second ADC should start at 2 TS and so on, right? The time delay should be TS.
Yeah, but like when we started, the example of sampling at 2 GHz.
That was, yeah, correct.
And when we use second ADC, we introduced a delay of 1 by 2, that is 0.5.
Correct. So 1 by Fs, right? That is TS.
Yes. So we had to sample at fs by 2 in like bandwidth problem.
There is no bandwidth problem.
No, when we needed to resolve the issue of bandwidth, we needed to sample at fs by 2.
I'm not getting your point, right? I mean, finally the ADC needs to sample at Fs, right? Which means the input should have a bandwidth till Fs by 2, right? Okay, so let's circle back. So what I was getting is when we looked at 2x interleaving, we had impulses at these frequencies. We were checking the phase of these frequencies. Now I am having impulses at these frequencies. I should be checking the phase at these frequencies, right? Now 0 is something fine, that is okay. We'll look at the rest of this kfs by n. For the first path, it is 0, no worries. Second path, it is e power minus j 2 pi. F I will replace as kfs by n times ts. So what will this simplify to? Fs and ts go away. This is basically j 2 pi k by n. Now by extension, what will be the phase added by the third path? if I have a delay of Ts, this is the delay, if this is the phase, if the delay is 2 times Ts, what will happen to the phase? It will just double, plus it will keep happening till I reach and from whatever you learnt in your 9th standard complex numbers, what is this equal to? Pi. Pi. Oh man. Okay. For k, any k lying in this range, what will this simplify to? Okay. Everyone skip 9th standard complex numbers, right? See, remember, this is basically like I'm taking a 360-degree circle. I'm taking n equally spaced faces. So I'll basically, do this. So essentially for a complex number here, I'll have an equal complex number on the other side. This will get 0. I mean, except for k equal to 0, right? For k equal to 0, this will all add up. For any k which is in this range, this will become. So as long as you have a case where the amplitudes in each of the paths is equal and you have this phases, all the interleaving images we have in each sub ADC, it will magically disappear at the output. So next time someone asks what is the point of learning complex numbers, you can tell if engineers didn't know this property of complex numbers, will not have high speed ADCs. It will take 2 hours for you to transfer a 10 MB file from laptop to your USB stick. That is basically a like exaggerated extension of this. Cool. So now this idea is clear now. Time interleaving, then main problem we can have is this and this interleaving images, and because of the phases and time delays, it gets cancelled. So now we have come up with something new. What do we do next? Yeah, we already named it time interleaved. I mean, usually we have some problem, we try to come up with a solution and then we check if it's working. So here we did it, we came up with a solution in time domain, right? And then checked if it's working in frequency domain, it is working. Then we'll see what all can go wrong in this. I mean, that's how you do anything in practice, right? And one thing you can clearly see that can go wrong is, if things are not proper, these cannot get cancelled. In practice, whenever something becomes 0 because things are getting cancelled, in practice it can't get cancelled completely. And under what conditions is it exactly getting cancelled to 0? One thing is, this assumes that the amplitude in each path is 1 and you have this exact phase. And what is giving you this phase in this time-interleaved ADC? The delay here. So the moment you have any delay in the gains in the amplitude or in the time delay, you will not be cancelling this interleaving images, you will end up with it finally. So that is one main issue. So if you have, let us say, timing error, or let us say gain mismatch, instead of timing error, I'll say timing mismatch. If you have either of this, you will have this interleaving images at k fs by n plus or minus fn for k going from 1 to n minus 1. So again, let's see in practice how this is tackled. So let's start with timing issue. So typically we write this. Typically we deal with it the same way we dealt with offset in the preamplifiers. How did we correct for the offset in our preamplifier? The area, but then we saw something, right? We did calibration. We'll try to do something here. And loosely, the basic idea of calibration is try to go and address the root cause or the immediate effect of the cause. So here the timing mismatch is arising. Why is it arising? I mean, when I say timing mismatch, it is because the delays of the clocks are not what you want. So what you try to do is the following. So let us say I have n clocks. Ideally, I want phi of t minus ts, phi of t minus 2ts, and so on. Okay. Now in practice, let us say this is some phi of t plus some delta t, say 0, phi of t minus ts plus delta t1, and so on. You are gone. So what we do is the following. We try to make sure the relative time shift between the clocks should be ts. That's what you want. So you can assume that the first clock is okay. With respect to the first clock, we'll try to keep all the other clocks spaced at ts, 2ts, and so on. Right? And one way to do this is you take, let us say, the clocks, let us say phi 2 to phi n. You give it through a variable delay line. And then give it to the ADC. You keep changing the delay of the clock until the timings are all okay. That's how we calibrate. You can use it, but there are simpler techniques also. Yeah, I mean, you can use, there is nothing wrong with it. So again, variable delay line is pretty simple. This is a digital signal. And how can you delay a digital signal? Yeah, remember, delay in your circuit is coming because you are having capacitors. You need some time to charge or discharge the capacitor. It's a digital signal. You can basically buffer it like this. And let's say you put a capacitor. Now you can go and change the capacitance value, for example, or you reduce the current pushed into the capacitor or increase the current pushed into the capacitor to play with the delay. So you can do any of this. This is one, like trivial way to do. But the crucial part is you will not know what is the time delay you should have before. Okay, so this should be corrected in the runtime. So what you will have to do is this. This is one brute force way. You have this entire time-interleaved ADC. Let's say you feed in a sinusoid at Fn. If there is a timing mismatch, what are the spurious tones I will see at the output? Huh? If I have timing mismatch, what are the additional tones I see? Remember, these are the interleaving images, kfs by n plus or minus Fn. So these are the unwanted tones I will see at the output. So what you have to do is the following. In English, you have to look at the strength of the tones and then do something and change the delays of the clocks until the strength of these unwanted tones is reduced to a lot, reduced to whatever level you want. So there should be some kind of an algorithm or some kind of a calibration engine running here that does this in the runtime. I mean, that's why I say, as a circuit designer, you should also have some basics of signal processing, right? Because here you will have to end up with using some kind of a least squares or least mean squares or some convex optimization. It's not necessary you should know the details of this, but you should at least know what I should put here so that I can do this. Because this notion of digital calibration is ultra common in circuit design. Any analog RF mixed signal circuits you see, even in your practice right now in your phones, smartwatches, lot of calibration will be happening in runtime. Because the common saying is, any non-ideality you have in analog, you'll say let's calibrate digitally. That's the common saying. So you should have some basics of what needs to be done. Again, I'm not explaining this. I mean, it's not like, I can go and ask you in the exam, what should I put here? That is not the point of this course. I'm just trying to give you a broad idea as to how problems are solved in practice. So this is about timing error. Similarly, you can have the same scenario if you have gain mismatch. So which means Ideally, you expect that all ADCs to have the same gain. But let's say this guy has a gain of K1, this guy has a gain of K2, and this guy has a gain of Kn. So, can you suggest something to correct for the gain error here? In English, what do you think I can do? And don't worry about implementation. In English, what can I do here to get rid of this error? I mean, why am I having this problem now? I have the gains to be different in each of these channels. So, in English, what should I do? No. Reduce the? I mean, don't be very generally, right? The gains are all different. If you, let's say, throw this problem to the third standard kid, right? Gains are all different. I should solve it. What should I do? I should make them equal. That's all. It is not necessary that all the gains are 1. All the gains in all the channels should be equal. So again, as usual, you can assume one of this to be a reference channel. Assume this is all okay. We will try to keep the gains in other channels to be equal to this. This is in English. Now in circuits, how can I change the gain? Let's say you can't touch the ADC, okay? So if I want to change the gain, what do I do? Huh? Sorry? Negative gain. Okay. Let's say you, why do you want to use negative feedback? No, but this is not an amplifier as such, right? This is an ADC in which there is some gain error. So again, you want to keep the, let us say you take only these two channels. Here the overall gain must be equal to what? I should make this equal to K1 somehow. Right now the gain is K2. What can I do to make this gain? Multiply by? K2 by K1. No, sorry, K1 by K2, correct. And where can I add this gain now? Yeah, I mean there are two places. I can either add here or here. So you can do either. So let us say here I go and do it in the analog domain. I have a variable gain here to change it, and I can do the same thing. So of course, many times this might not be feasible because changing gain in analog is tricky. What is the simpler thing to do? Huh? Comparator. No, comparing with reference. Yeah, that's what you have to do, right? See, somehow you will change the gain here to keep this gain to be equal to K1, right? But what I'm saying is changing the gain in the analog domain is difficult. Where else I can change the gain in this system? At the output also I can scale it, because in digital multiplication is trivial, right? I mean just left shift, right shift and it's all done. And that is something commonly done. So what you do is this, instead of putting this, you again have a programmable gain here in digital, and that's actually straightforward. But once again, the real problem is you do not know what gain you should put exactly beforehand. This has to be done in the runtime. So what do you suggest we can do? I mean, how will you figure out if the gain you have is right or wrong? You can't compare the gain. I mean, you can't measure the gain of this itself, right, directly. Yeah, right. I mean, see, always think, right? You are doing all this business for what? I started this entire thing because of the mismatch. If I fed in a tone at Fin, I saw all the interleaving images at KFS by n plus or minus Fin. So again, one brute force way is to check the strength of this fellow, have a kind of an optimization engine that goes and changes this. This is how we'll have to opt. Yes.
It must not be feasible to realize all those variable buffers at the output.
At the output, it is not a buffer; it's a digital number. multiplication with a digital number is trivial. It's a simple multiplier.
Like 10 times.
Yeah. I mean, see,
There must be many ADCs, right?
Yeah.
Having all these.
the multipliers need not be changing, right? Basically, the point is, this is a digital logic. This need not run at the same rate as FS. This can run at a much lower rate, let's say FS by 1000. So which means this will slowly correct the error, but once it corrects, it is okay.
For that, we need some kind of form
Which one?
to detect particular ASS.
Yeah, something. Comb filter, or I'm just telling you in English. This is all signal. This is solution in English. Now you translate to a signal processing solution.
So this is how many times this happen in field devices?
It depends. I do not know, right? But typically it won't be running at really high speed. This will happen in the background at a much slower rate, because it's not like the mismatch will keep changing so much with time, with temperature. It will drift with temperature, but not very fast, because it is not like at this instant you will be here and the next instant you will shift to Antarctica, right? It will take some time, and by then it will. Cool. So one last mismatch we can have is this. Let's just look at it. So as you guys know, by this time ADCs can have offsets, and the issue is offsets in each channel can be different. So let's see what happens because of that. I copied this, great. So the last issue that we will discuss is offset mismatch. So which means now the problem is each ADC has an offset of something. Let us say the first ADC has an offset BOS1, second has an offset BOS2. So first let's see what happens if there is a mismatch in the offsets. Okay, this is Y, the output is V, and each ADC is running at Fs by N. Okay, so ideally what should be the outputs I get here? If the input is Y, at the output I'll get Y of 0. That's all, plus a quantization noise. Let's ignore that. The next sample will be Y of N. Okay. Here I'll get Y of 1, Y of N plus 1. This is Y of N minus 1, Y of 2N minus 1, and so on. Now if my ADC has offset, in addition to this, an offset is added. So this is VOS2. This is VOSN. So finally, when I stitch all this N digital data to form a final data stream, the first sample will be from here, second is from here, and so on. So if I look at the final data, you'll have, let us say, Y of 0 plus VOS1, Y of 1 plus VOS2, okay, so on. And then after N samples, I'll come back here, right? So this will be Y of N plus VOS1. This is the final data I'll have when all ADCs have offsets. Things are fine till this point? Okay. So now I can decompose it like this. I'll rewrite it as the ideal sequence I should get. Okay, this is the ideal sequence I should get without offset, plus an error sequence. And how will this error sequence look like? Yeah, remember, this is the actual sequence I get. I am trying to write it as the ideal sequence I want plus an error sequence. The first sample is Y of 0 plus VOS1. Yeah, so the ideal term has Y of 0, the error term will have VOS1. What will be the second term? Second channel's offset will come, and then the nth channel offset will come, and then it will keep repeating. Fine. So this is the error sequence. So in addition to the write data, I am adding an error, and this error is a periodic sequence or a non-periodic sequence? Periodic sequence. What is the period of the sequence? So n samples, it has periodicity. So if I have a periodic sequence with n samples periodicity, if I look at its frequency spectrum, what will I see? If you have a periodic signal with some fundamental frequency, if I look at its Fourier series, what will I see? Huh? At what frequencies? Okay, what is the fundamental frequency here if I call it omega naught? 2 pi by? Fine. So this is the fundamental frequency. What did Fourier say? You will see the harmonics of this fundamental frequency, right? So in addition to the actual signal, you will see unwanted tones at k times 2 pi by n. Fine. Again, if you translate it to a continuous time frequency, what will this be? Discrete time it is k 2 pi by n. In continuous time it is k times, remember 2 pi is fs, right? So that's what is going to happen if there is a mismatch in the offsets. In addition to the ideal spectrum at the output, you will see all these spurious tones at all these frequencies. Cool. So again, this is not something you want, so we'll have to go and correct for it, and copy this. And how do you suggest we will be doing this in practice? I mean, again, in English, the issue is because the offsets in each channels are all different. So what is the solution? I should keep the offsets in all channels to be same. As usual, I can choose, let us say, this as the reference channel, and try to keep the offsets in all of them equal to VOS1. Now translate that in circuits. What should I do? This has an offset of VOS2. In the final path, I should ensure that the offset is VOS1. No, offset is getting added, right? Huh? In principle, in this path, if I somehow add VOS1 minus VOS2, I am set. Again, how many places I can add this now? At either this point or at this point. Which do you think is easier? Digital domain, you can generate any number you want in the world. It's not something you can do in analog, so you try to add it here. And as usual, you don't know how to, what should I add before? So what will you do? You apply a tone at Fin. Now because of the offset mismatch, we saw that we will have spurious tones at k times fs by n. You observe the strength of the tones at these frequencies and then do something and go on correct.
Or we will give a constant signal for 2 time periods.
Sure, that's also fine. Yeah. You can also give a constant signal, and the output will be basically 0, and then you will have unnecessary stuff. Yeah, this is just a brute force way. This is not the exact way in which it is done, right? The idea is this: you apply some known signal and see, correct for the non-idealities at the output. Good. So that's what I wanted to discuss on time-interleaved ADCs. So to summarize, the idea is the following. So if you have an ADC operating at Fs by n, and you want to realize an effective ADC running at Fs, the principle is use n of them in parallel and make sure that the clocks are shifted by k times Ts, right, where k goes from 1 to n minus 1. And the main non-idealities we can have are these. You can have gain error mismatch, timing mismatch, or offset mismatch. Right? And just to remind you, when you do this interleaving, in each sub ADC, there will be aliasing. You will get all these interleaving images, and this exactly gets cancelled provided the gains are 1 and the phases are all this. So whenever you have a mismatch in the gain or in the time, that translates to a fact that at the output you will see these aliased components. So in either of this you will get unwanted tones at this frequency. Again, k goes from 1 to n minus 1. And if you have offset mismatch, you will have spurious tones at k times Fs by n, k goes from 0 to n minus 1. Clear? So I'll just show you a couple of examples in the literature, and then we look at some spectrum calculations so that you get a hang of it, because that is one of the practice sets problem. Yeah, you can see it, right? So yeah, this is basically in the Journal of Solid State Circuits just last year, and as you see, this is used in a wireline receiver for probably some standard 802.11 some thing, and this is all from Intel. Okay, I mean you can see this is from Intel. Everyone is from Intel from different countries. So, and Intel is one of the companies which has been trying to make this high-speed serial links, and as you see, they use a 6-bit ADC, so 64-way time-interleaved ADCs. So in a way you can say, I mean, if you want to increase the speeds of the serial links, you definitely have to make a higher speed ADCs. Because that is not the only thing needed, but that is also needed. So I'll also show this one. This is another paper again from Intel. Again, this is also in last year. So this is also from Intel, I think. Yeah, Intel Hillsboro and Santa Clara, and even people from Intel India, right? No, it is not sharing the information, it is advertising the work. See, this solid state circuits is the place where any groundbreaking research you have, any groundbreaking product result you publish. I mean, they just show the final result, they will show what they have done, but it will take years for you to replicate, right? I mean, just because they showed this work, they would have started 5-6 years back, I mean, probably 3-4 years back, I don't know, right? So just because they show it now doesn't mean, you know, like a competitor can immediately copy. By the time they will be already in market. So this is just on high-speed ADCs. Again, as I mentioned, the interleaving is a general principle. So here they are using in a SAR ADC in time domain. We'll see that later. So let's just focus on the output spectrum and make some calculations. Yeah, this is the final measured spectrum. Yeah, let's look at the one on the left. Okay. So here, this frequency is 1.9 gigahertz. So what do you think the sampling rate is? Twice that. This is Fs by 2, so this is 3.8 gigahertz. Okay. And the input they have given it's 0.2. So firstly, where will the third harmonic lie? 0.6. No aliasing, no worries. And here they have used a 4-way interleaving. Okay. So if there is a mismatch in the gain or in timing, what will be the additional frequencies I'll observe? K plus or minus Fn. Okay. and in this case n is 4, so basically it's k times 3.8 by 4 plus or minus 0.2. This is k times 3.8 by 4 0.95 plus or minus 0.2. At least for k equal to 1, this becomes what? Yeah, 0.75 and 1.15, yeah? Correct? So this will be the tones you see if there is a gain mismatch, and this is the third harmonic. And what if there is an offset mismatch? You will see tones at k times fs by n, that is basically k times 0.95. Fine. And as you see, magic eraser. So let's verify. So HD3 is 0.6 somewhere here, and if you have offset mismatch, we'll have 0.95 somewhere here. This is the offset mismatch. Similarly, if you have gain mismatch, we saw at least we should see two tones at 1.15 and 0.75. So 0.75 is somewhere here, 1.15 is somewhere here. So let's also do one more calculation, because this slightly you have to think. Okay, cool. So here again the same setup. Fs is 3.8 gigahertz, but my input is at 13. So where will you see the input frequency? I mean, okay, 3.8 tables, I'll write 3.8, 1 is 3.8 times 2 is how much? 7.6 times 3 is. So now tell me, where will it fall? I mean, yeah, it is 11.4 plus 1.6 is 13, right? So 11.4 is 3 times fs, okay? 3 times fs plus some delta f, that will alias to delta f, so that's what you have at 1.6. Okay. And similarly, where will the third harmonic lie? Fn is 1.6, okay? Third harmonic will be at, I mean, first of all, 1.6 times 3. Okay. 1.6 times 3 is 4.8. Yeah, it will alias to? It will alias to what? Fine. And what about mismatch errors, gain mismatch? I'll have k times fs by n plus or minus fn. This is basically k times 0.95 plus or minus 1.6. For k equal to 1, where will it lie? I mean 1.6, let us say minus 0.95. Okay, first let us say 2.55 and 1.6 minus 0.95 is 0.55. Fine. So 2.55, will it fall in the bandwidth or no? It will alias. Where will it alias? 3.8 minus 2.55. So what is this? Is 5. So we'll have these tones. Similarly, if I put k as 2, I'll put here. If I put k as 2, I'll have 1.9 plus or minus 1.6. If it's negative, it will be at 0.3. Positive 3.5. So where will 3.5 alias to? That will also be. So finally, you should see at least these tones. So let's again do magic erasure. So let's see. First of all, third harmonic. Where did it lie? Third harmonic HD3 is lying at 1. So roughly around 1 gigahertz you see. Okay, because the frequency is not exactly 13, it is rounded off, right? Because you have to ensure this m by n times fs. It might be 13.01, I do not know, something. So about 1 gigahertz you see the third harmonic. And because of gain mismatch, you should be seeing one at 1.25. That is probably this one. You should see one at 0.55 somewhere here, and one at 0.3. That should be this one. So I mean that's why it. I mean now if you look at the ADC, you'll have whole bunch of tones, especially when you interleave. You should have a clear idea as to what each tone from where each tone is arising from, right? And especially if you are checking with inputs close to fs by 2, you will have a lot of aliasing. So you should be very fluent in understanding and locating where each of these interleaving tones or spurious tones will fall in your spectrum. Cool.
And here, these 5.
Which one V5?
And
Why should n is their choice,
now
right?
is 5.4.
Enob is 5.48, but n here is the number of channels that are interleaved, right? They are interleaving 4 channels to get so much 3.8 gigahertz of speed and so much Enob. That's all. Okay, so I'll stop here.
Can you go back?